continue over there. Good morning, everybody. Welcome to our CS 181 course. How's everybody doing? Good. Excited for fall break? Yeah. It's really cold in here. Yeah. Yeah, it's really hot outside, really cold in here. I always forget about fall break. It's always a nice surprise to me when students remind me that I'm scheduling a quiz on a holiday in my other class, and I can't do that. But let's see. So we were talking about last time this thinking like a transformer stuff and this Rasp language. And we'll do, again, a quick review of all the stuff that we talked about last time, and then get into the actual cool stuff this time. So last time mostly talked about the starting here at this primitive sequence operations. There's a whole bunch of like weird syntactic stuff about Rasp. Maybe let's make this one size bigger. Bunch of weird syntactic stuff about Rasp. The most important distinction here is between a sequence operation and a function. They look the same, but they're not the same. The sequence operations are the most important thing in Rasp. Everything else that exists in Rasp is for constructing sequence operations. And we haven't talked about it yet, but a sequence operation has a bijection between sequence operations and transformers. So that means that for every sequence operation that you can code up in Rasp, there is a transformer that can be learned from that. And for every transformer that can be learned, there is a corresponding sequence operation that could be programmed in Rasp. So normally when we're doing transformer stuff like ChatGPT, whatever large language model you're using, it was not programmed in Rasp, but it could have been in theory. It would have been very, very difficult to do, but it could have been in theory. A lot of weird gotchas throughout here about just syntactic things that we talked about last time. And again, does not exist any explanation anywhere else in the world about these weird syntactic things. It's just the author of Rasp, Gail Weiss, assumed that she was writing this for other researchers, people who have experience with dozens of programming languages and would already know ahead of time like what the weird edge cases might be on something like this. The basic control flow stuff here is the most important, like fundamental concept about Rasp is that it is not procedural. So things like Python, basically every programming language that you've probably been exposed to, with the exception of SQL, is a procedural language because things happen one step at a time and you're somehow telling the computer what the procedure is for doing something. Rasp is not that way. And in particular, like the if statements and the functions and the for loops are not, they don't behave anything at all like they do in Python. If you've heard the word macro in programming languages before, it comes up in a handful of situations. C, C++ is the most common way that the word macro comes up. Other scripting languages for games often have the word macro thrown around. Technically, the functions in Rasp are macros and not functions. The high-level distinction between that is a couple of distinctions. One is that macros are literally copied and pasted and not, there's no like stack, there's no scope of variables, other things that you might have, random terms you might have heard before. But all those things are necessary to do interesting things with the functions like recursion, and you can't do any of those things is the takeaway. The if statements, the if statements things that you definitely have to use to implement things, but they work differently. Again, they're ternary. So the thing on the left over here of the if statement, this is the true value. This is the condition to the right of the if statement, and the else is the false statement over here. Unlike Python, where you can have an if statement without an else statement, in Rasp, you have to have, if you have an if, you must have an else. And that's because both these branches will be computed. There's no way to only compute one branch and not the other. Both of these two things will be fully computed in Rasp. Yeah, again, the function or macro definition syntax here is different than, or it looks like Python. looks like these things, max and min, sort of like sequence operations, but they're different. So don't get those confused with the SOPs. And then the complex control flow, everything up here from a language perspective is uninteresting. In the paper where Gail Weiss explains Rasp for the first time, none of this stuff up here is mentioned at all or maybe has like one sentence that summarizes everything up there. And she's given a handful of tutorials about like what Rasp does. None of that stuff ever gets mentioned in those tutorials. And language people consider all that stuff uninteresting. It's necessary to get something done, but it's uninteresting. The interesting stuff here is this complex control flow where we sort of left off last time with this select and the aggregate function. And what really makes this interesting is select and aggregate are going to give us like a very strong limitation on what we can do while we're programming. So things like for loops and while loops give us a lot of power, a lot of flexibility, control about what we're doing. Select and aggregate give us a lot of restrictions on what we're doing, make it really hard to accomplish the task that you want. And so in some sense, it's amazing that like we can do anything at all with these like very strong restrictions. And understanding like in principle what a transformer is capable of accomplishing is somehow equivalent to understanding what these select and aggregate functions are capable of doing. So last time we talked about where we left off was the mechanics of what select and aggregate do. We'll review that again really quickly today, but then spend most of today talking about the like semantics or the why we should care about select and aggregate here, and what's the like how can we use these to accomplish certain tasks, and how can we not in principle use these to accomplish other tasks? What tasks are out of bounds for us because of these select and aggregate functions and their limitations? As an aside, this is like what I consider to be like real computer science, where you have a new programming model that has some sort of weird limitations to it, and trying to understand like what are the capabilities of that programming model. That is vast majority of CS research somehow falls under that category of you have an interesting programming model and what are the real limitations of that programming model. Okay, so complex control flow here again. So no analog to these functions in other languages like Python. Not all programs can be written using these functions. But again, if you understand what programs can be implemented with these functions, then you understand transformers and what they can do in principle. Again, this is what they can do in principle, and there might be other training issues which further limit what they can do, but no amount of clever training things can get around the fact that if something can't be implemented with select and aggregate, then it can't be done in a transformer. Okay, let's see. I'm going to try to do things side by side here again for a little bit. Let's see. So on the left-hand side, I have my terminal open into my Rasp folder. I'm going to do something I haven't done before, I don't think. I'm going to export ps1 equals $space. And so that just changes the prompt over here that I am using for my terminal command. $, a classic prompt. Other things usually before the $, but anytime you see a $, that means we're typing something into the shell over here. And I'm currently in my Rasp folder, has all of the standard stuff in the Rasp folder. And starting up Rasp, we can do this with this /rasp.sh. And now I'm typing in Rasp commands down here. Let's see, where did I go over here? Complex control flow. Let's remind ourselves what this select operation does. So first of all, tokens is this the input to our transformer. The only primitive SOPs here are tokens and indices. These are the only things that the input to a transformer can receive. What are the individual tokens and where are they located? And the select operation here is the only thing that operates on something that is not an SOP. Select takes two SOPs as input and then outputs this matrix looking thing. So select tokens, equal, like this, gives us this matrix looking thing over here. In this case, the rows and the columns happen to correspond to the input over here, tokens and indices. But we saw last time that again, these SOLangs often have non-ergonomic features for them, and so this is always going to be the tokens listed up here, and not necessarily the actual thing that the select operation is doing. So we have the rows and the columns here, and then the operation over here that we're allowed to pass in. We can do any Boolean sort of comparison operation, like equals, less than or equals, not equals, but those are the only operations we're allowed to do, something that results in a Boolean value comparing these two elements. So here we did an equal sign, and we said H and H, that's equal, so we get a 1 here representing true. H not equal to E, so we get a blank here for false. If we do indices, comma indices, then this gives us the full diagonal matrix here. Again, it's displaying the tokens up here, even though I'm doing it on indices, but this gives us a diagonal. And if we change this to a less than or equal, then that gives us like a triangular thing, lower triangular, or greater than or equal to give me an upper triangular thing. We don't have to only compare the indices like this. We could compare the tokens, and it'll do it ASCII-betically, tokens like this. And this is what for this particular input right here, what the ASCII-betical comparisons happen to be. I asked you guys last time to try to play around a little bit, get yourself comfortable with these select statements and what they're doing. But any questions at this point about the mechanics of the select statement? Yeah. So it is possible to, so up here, you can't do and or. The equal sign would be equivalent to and, the not equal sign equivalent to X or, and then you can combine things together with, if we have select tokens, comma tokens like this, and let's do that, or select indices, comma, less than or equal to. So the right hand, this select statement right here is the lower triangular matrix. This one over here is this matrix up here. And we can, the output of these matrices, even though they look like they're numbers because they contain numbers in the output over here, that's just for visualizations purposes. And these are actually true and false values over here. And the selectors, which are these matrices, the matrix and selector synonyms for each other, those are the outputs of the select statement. These selectors, they can be combined using standard Boolean operations. And so if we do that, then we get it's the lower triangular plus this one additional thing here, which is the equals between the L and the L right here. And it turns out from that, you can implement a lot of different things with some clever tricks, but you can't directly, it doesn't directly do it. Yeah. Good question. Any other questions about the mechanics of these selectors or select statements so far? Okay. Again, yeah, this gotcha right here. Anytime, or there will be some tasks that you have to implement for your homework assignment, and in some of those tasks, it will be tempting to try to provide a input sequence manually, something like this. You can't do that in Rasp because the code that you write has to be generic for all possible sequence lengths. And so if we do something like this, try to manually create a sequence, you'll get a weird looking error message. So this never allowed in Rasp. These two things have to be SOPs and nothing else. It will work. Let's see. So let's say we talked about already how you can combine selectors with the Boolean operations like here, like the OR. Again, it looks like the output of something like this would be numeric because it's being displayed in numbers, but you can't actually do numeric operations on this. So something like this, taking a selector over here, a Boolean matrix, and multiplying that too, that is a type error, will give you a error like this. One of the few actually helpful error messages that we get right here. Okay, so selectors by themselves, not helpful or not useful. They're useful in combination with this aggregate function, which takes selector and converts it back into an SOP. Again, the SOP is like the fundamental unit of these Rasp programs. They have this bijection somehow between selectors and transformer architectures. And so in order to get back to the selector, in order to get back into the transformer architecture, we have to use this aggregate function. And so last time we talked a little bit about the what does. Again, we'll review that real quick and then get into the why and how you use it, the why and the how. So in many programming languages, patterns started with Python, continued in Rasp, and a lot of these SO lengths is that if you want something to be sort of local variable, then you prefix it with an underscore. And so if you're just creating like a temp variable to do stuff with, then put an underscore in front of it, and then you're this is the real thing that we care about right here. But anything that has an underscore is just like a helpful helper variable here. So we're going to walk through the mechanics of how this aggregate function applies to this selector here. So the underscore selector is this lower triangular matrix. Again, indices compared to indices with the less than or equal to operator here, creating this lower triangular matrix. And then we'll aggregate this selector with indices like this. And what aggregate is going to do again is it's going to take the average of this whatever sequence we have here on the right-hand side, do an average of this where it only considers the elements inside of this sequence if there is a 1 in the corresponding location over here. So in the first row right here, like we're mapping indices onto here. Maybe before I actually run this, let's just remind ourselves what indices looks like. Indices like this from 0, 1, 2, 3, 4. So the indices position at this position right here is 0. And we ignore all of these other blank spots because they're false. They're not equal to 1 in the output right here. And we average 0 with itself. We'll get 0 for the very first entry in our result of this call right here. Down here, we'll have two things that we're averaging together listed by this mask of 1. So we'll average the 0 and the 1 together. And so the second position will have 0.5, average of 0 and 1 together. Down here, where the mask contains 1s and everything, we will average all of these results together, and that'll be like 2-ish, probably. So we'll run that here like this, and that's what we got. The 0 comes from up here because we're only averaging the very first token right here, only taking 0, and then 2 down here because we're averaging everything in the indices, getting all of this right here. It took me, I don't know, probably a half hour of just playing with a bunch of different examples before I felt like I had a remote intuition at all about how combining selectors and aggregates would interact with each other. So it's the sort of thing that you're not going to get an intuition from just from looking at other people do things. You really have to just apply these things to different situations, predict what's the output going to be, and see if your prediction was right or not. Any questions so far about the mechanics of the aggregate function? Yeah.
So, if you're aggregating
yeah, that's a good question. So here, the first of all, the types into aggregate, it's always going to be a selector on the left-hand side and an SOP on the right-hand side. And since aggregate is doing an average, then in some sense, the thing over here on the right-hand side has to be numeric because it doesn't make sense to say average Boolean variables or average strings. Aggregate, let's do see what happens if I do aggregate tokens right here. So tokens again is a list of strings, and we'll get this something went wrong error asked to average multiple values, but they're non-numbers. So yeah, you can't, if you have aggregates, when you're using aggregates in your selector over here, the most straightforward thing to say is that you can't apply a non-numeric thing, non-numeric SOP over here. It turns out, though, that if there is only one thing that you are averaging together, then it's always the case that you can convert everything inside of tokens is stored as a number. You can always convert those tokens into a number, convert this L into, it's going to be like 70-ish ASCII. Convert that into the ASCII number, average that with itself, you get 70 back, and then convert back into the tokens. And Rasp will automate that process for you. So let me create a new selector. I'll call this underscore selector new is the select of indices, comma, equals like this. So it is like our identity. And when I aggregate that, aggregate this, because there's only one thing in each position, it will be okay to do aggregate selector new, comma, tokens. That will be okay because now when you're doing this average, you're only averaging, like, say, in this case, E with itself. And so you won't get a type error there. This is just a syntactic sugar sort of thing. Like actual implementation is it takes these tokens, goes back to the corresponding number, averages it with itself, which is nothing, and then converts it back into the string type. One of the few syntactic sugar sort of nice things that the Rasp program does, automates for you.
Can you go an example of why there is 1.5 there?
Why there is 1.5 there? Where are you talking about?
On the aggregate function. All the aggregate functions is like the example of hello 0, 0.5, 1.4.
So let me
I think it would be like this. So
rerun both of those two things. Answer your question here, where does this 1.5 come from? Yeah, it's a good question. Again, like it just takes playing around with these things to really get the comfort with this. So here in this case, we have 1, 2, 3, 4 Boolean values right here, all corresponding to the first 4 entries in our in whatever sequence we pass into aggregate. In this case, we're passing in indices to aggregate. And so when I do indices like this, then I'm averaging the first 4 of these numbers together. I know it's the first 4 because it's these 4 up here. And so the average of 0, 1, 2, and 3 happens to be 1.5, and that's where this 1.5 comes from.
When you do the average, like, what does it do? If the total number is 5 numbers, right? So it would be 6 over 5.
And then the number that it averages by, the denominator of the average is the number of Boolean things up here.
Okay. Then when you sum it up, it's 6 divided by Boolean values, which is 3.
So yeah, 6 divided by 4, 1.5.
Oh, okay.
Yeah, so that's a important thing about Rasp. It turns out that you wouldn't be able to implement anything at all if it was always dividing by 5. Very important that it ends up dividing by the number of Boolean values up here. Good question. Any other questions so far? Yes, Ron.
Yeah, is there any way to force my aggregator to look at like the ASCII indices of tokens? Or?
To look at the ASCII indices of tokens. I'm not sure what you mean by that.
Or like the ASCII number instead of like the letter value.
So the question is there a way to convert from the ASCII to the the letter value to the number representation? I'm guessing that this will work. Let's try this. It does not work. Maybe there is, maybe there's not. I'm not sure. It's not something that is, I guess, interesting to do in any case. It's something that you would need to do to implement like a real program, but the purpose of Rasp is not to implement real programs. So it is doing it under the hood here. My guess is somehow it exposes an interface to do that, but I don't know what it is. And there's no documentation for that. I'd have to read the source code to figure it out. I mean,
I know, we just want an example where we can use like the aggregate function selector and like that's like the specific example. Generally, it would be used with like selector.
So the question is, like, generally, what goes on the right-hand side of the aggregate function? And the answer is that it could be indices, could be tokens, could be any arbitrary SOP. I would say that, so we'll see some examples here in a little bit. Again, walking through the why and how of these things to accomplish bigger picture tasks. I'd say a vast majority of times it's something more complicated over here that you have constructed previously. Let's see. One last mechanical example of things to do with aggregate, and then we'll get into the why and how and the cool parts of the aggregate. Try to get an intuition about like what you can actually build from this aggregate function. The mechanical example here is what happens if there is nothing to average together. So let's make this be our selector with the less than sign over here, and let me clear our some space here. So with the less than sign instead of less than or equals to, and now in this first row up here, there are no true Boolean values. And so then like, what does it mean to take the average of an empty sequence that's sort of undefined? And aggregate it's overloaded to be able to have 2 parameters or 3 parameters. The third parameter is what the default value would be if you're taking the average of nothing. By default, if you don't pass in that third parameter, the Rasp will use a 0 value here. So here there's nothing to average together, so it puts a 0 in the first location, no matter what value, what SOP you pass in right here. But if you want to change that, you can add this third parameter right here. So we can do this with 42 instead, and now this first location is 42 instead of 0. That does turn out to be something that is necessary to do to implement certain types of functions in Rasp. So this actually adds computational power to your programs, being able to specify a default value right here. Okay. Any last questions on mechanics before we get into examples of why and how? Probably there are some like lingering questions about the mechanics of things, but hopefully talking through these examples will help illustrate some of these, the why and how things. Okay, so in this section, again, the purpose of these examples to help understand why to use the aggregate in the select functions in different combinations. One of the simplest programs that the Rasp standard library defines is the length SOP. And so let's go ahead and down here, we'll just see what exactly it does. And then after we see what it does, we'll walk through the implementation. So here, if I do length semicolon by itself, again, this is an SOP. So if you don't provide a input to the SOP, then it uses whatever the current example is. The current example is hello. And the output here is 5 times 5. This is an annoying thing to me, but the output of Rasp, whenever you have a sequence that is all the same, it uses this Python string or list multiplication syntax to just say what the element was once and not list it out many different times. So here, what this is saying is that the output right here is, I'll make this bigger for a second so it's all in one line for a second. The output of this length on the hello input is the number 5 repeated 5 times. If I do, again, indices, it's going to give me, because these are different values inside of here, it's going to give me those values actually explicitly. But if I do something like indices times 0, then indices times 0 is 0 everywhere, so it gives me list 0 times 5. So Rasp, for whatever reason, in the output down here uses this multiplication syntax if you only have the same value repeated many times. The length SOP, what it does is however long your sequence is, it stores that length in every position of the output. So here our input was 5, and so we have 5 repeated 5 times. If we had length of, so hello world, a longer input right here has 11 characters inside of it, so it has the number 11 repeated 11 times. In something like Python, if you were to implement a length function, you would have the output just be a single number. But again, in Rasp, the SOPs never change sequence size They always have the same length. And so a common pattern is that if you have something that feels like it should be outputting just a single number, then you output that single number everywhere in the position. Every position is going to have that number. Before talking about the implementation of this length SOP, any questions about the understanding the output here of the SOP and what it means? Everyone's tracking? Mostly?
Why did you like 11 times 11?
Yeah, so the question is, why is it 11 times 11 right here? And this is, let me go into Python for a second. So enter Python right here. And if I have in Python, you can do something like this, where you have a list and you multiply it by number, and it repeats that number that many times. Something like list of 0 times 11 repeats that number 11 times. Because I was in the habit of semicolon terminating my things from Rasp up here. In Python, semicolons are optional. You've probably never seen Python code with semicolons in it, but you are allowed to put semicolons at the end of Python lines. So this syntax right here is inspired by Python. A lot of the syntax things inspired by Python in Rasp. And it just means that it's this number repeated this many times. The output of length, let's see. As a computer scientist, one of the things that I like to think about is what are some invariants that different procedures must obey. And one invariant of this length SOP is that the contents here of the square bracket will always be the same as the number that we're multiplying by, because the number that we're multiplying by is the length of the string, and what length is computing is the length, and so it's going to put that number over here. Did that answer your question? Back into Rasp. Okay, so the length here is something that we could in principle have our transformer have that as input into the model, somehow adjust our model so that it's getting the length as input, but no transformer architecture does that. ChatGPT does not do that. BERT does not do that. No transformer that's ever existed does that. And so if for whatever reason what's going on inside the transformer needs the length, it's going to have to do a computation that's going to look something like this big messy thing over here. And so let's walk through step by step what's going on with this messy thing. So the first part here I want to talk about is this full underscore s. Full underscore s is a selector that is built into Python. It's part of the standard library. Built into Rasp, part of the standard library of Rasp. And when I say that it's built in, I don't mean it's one of the primitives. I mean that it is constructed for us automatically, a very common thing to use, so we don't have to construct it again ourselves. The definition, actual definition of full S right here is select 1, 1, equals. So again, recall that when we place a number inside of select instead of an SOP, this number is broadcast to the length of the SOP. So this is the sequence of all ones on both sides right here. Totally ignores the input tokens and indices. Sequence of all ones, and we compare to see if the corresponding positions are equal to each other, and they are. So it's a common thing to need to use in SOP computations, and so the standard library defines full S. Full S equals this thing up here. I think Rasp will give me an error if I try to redefine it. Can't set reserved name, but that is the actual definition in the standard library. And so we're aggregating somehow over a matrix like this. And so when we aggregate over a matrix like this, where we have ones everywhere, we are going to be averaging everything in our final SOP over here. So full S means average everything in your SOP over here. Let's take a look at what this SOP looks like. So indices, we'll break it down again, starting with the inner parentheses here. Indices equals 0. Indices equals 0. This gives me true in the first location, false everywhere else. And the indicator, again, converts Boolean things into numeric things. So indicator of this gives me a 1 followed by everything else. We're going to try to average this together. So use the selector up here to decide what to average together down here. And when we average these things together, we're only going to consider like one of these actual locations, or there'll be a 1 in one location and a 0 in every other location. And so when we aggregate that, get my parentheses matching, what that actually gives me is whatever 1 divided by the length is equal to. In this case, the length is 5. So there are 5 things here in my indicator SOP, or my indicator SOP right here has 5 things inside of it. All SOPs have 5 things inside of it because n equals 5 for hello right here. One of those things is equal to 1. The other are all equal to 0. So the average of this right here, the average of this is going to be 0.2, 1 divided by 5. In order to convert this number here into the actual length, that's what this 1 divided by is going for right here. So 1 divided by this whole aggregation gives me 5 as a float, repeated 5 times. And then the last thing that this code does is applying the round here to convert this float back into an integer. Round, convert that float back into an integer. So this length here does a very weird sort of trick here of using the average to compute the length of something. This is the sort of like weird thinking that you have to get into the habit of in order to be able to implement programs in Rasp. I'll say that the first time that I looked at this code, it again broke my brain for a solid 20 minutes as I was trying to figure out what was going on inside of here. So okay, if your brain feels a little bit broken about this, and like how would you ever implement that, like figure that out yourself. But yeah, seeing lots of examples, we'll do more examples. We'll have some exercises here in a little bit that will help you get into thinking the right way, thinking like a transformer. But any questions about the mechanics of what happened here, or anything about what happened here computing this length operation? Yeah, Rowan.
It kind of feels like in order to have full S, you would would need to go with the length of the sequence is, right? Like in order to put a 1 in every spot, you need to know how long it is, or is it not working like that?
So that is a true thing. That in order to actually compute this output down here that we are seeing, the computer needs to know what the actual input is. In this case, just to get the length here, but more generally in order to like be able to actually decide like where's the 1s and 0s. So full S itself is like a graph of computation. Full S itself is this code, select 1, 1 equals. And internally inside of Rasp, there's a data structure, a dictionary that associates the names of your variables with the actual code that is created for that variable. It does not internally store like a matrix like this. And then when we do full S, actually try to visualize it, then the Rasp interpreter takes this code and decides, okay, my current example is hello, it has length 5, and so I'll expand these to length 5 and display it down here. But if I do something like change the example, set example to something of length 3, and then do full S again, I don't have to redefine full S because full S is not this matrix. Full S is not the matrix. The selector is not the matrix. This matrix is just a visualization of the selector on this particular input right here. Full S is actually this piece of code right here. And so when I rerun it, we get this new selector like this. If I change the example to be something larger, hello world, then it gives me the much larger matrix like that. So internally, and the right way to think about all of these variables that you might be creating is that they are not the matrix that you visualize. We do something like, I think last time we did indices plus 1 equals indices plus 1. This indices plus 1, it is not the actual like string that we are seeing down here, this list sequence that we're seeing right here. This is just an example of what this would look like if we applied it to hello. But we can apply this to anything that we want. And it's what this actually is. It's the computation that converts this into this thing down here.
So if like the full string, in order to like create the presentation, I would think it would kind of need to have stored in memory somewhere like the length of the string that was creating the thing for.
So Rasp internally probably stores the length. I could think of ways to implement this without actually storing the length. But Rasp internally is allowed to do, this is a weird thing about these like weird computational models, is that Rasp internally is allowed to like break the computation, do things that are not allowed for us to do with just this interface right here. That the interface right here that's being exposed, the interface is what is like the transformer is implementing. Rasp internally, it could implement this with a transformer. It could implement this with a bunch of elves typing at their keyboard really fast. The easiest way to implement it would probably be to internally store the length of that somewhere. But that's not exposed in the interface anywhere because the transformer implementation wouldn't have access to that. Yeah, so the right way to think about, let's see, so we had this select 1, 1, equals like this. The right way to think about what this 1 is doing is the verb is it's broadcasting the constant right here onto the SOP. And so 1 itself is not an SOP. So if I do something like 1 plus 2 down here, these are not SOPs down here. These are constants, integers that are just being added to each other. But as soon as I do something like indices plus 2 like this, this 2 right here, anytime we have a number that is somehow needing to be in the location where an SOP is going to be, that number is being expanded to actually be an SOP, and then the things will happen component-wise. So here, this is the SOP, this 2 number right here is the SOP of 2 repeated n times, and that will be added to the indices component-wise. So this is sort of like a shorthand notation for something like this, which we're not allowed to do in Rasp because doing something like this, we'd have to specify the length explicitly. And doing something like this, we don't have to specify the length explicitly. Doing something like select 1, 1 equals, we don't have to specify the length explicitly. It turns out that so very random detailed aside right here, okay, if this doesn't make sense, anytime you're doing this sort of broadcasting operation with the constant value here, this corresponds to the bias term in a multi-class classification machine learning model that's internal into Rasp or into transformer architectures. These correspond to bias terms, and things like these actual SOPs correspond to like actual weight matrices. But detailed aside, that doesn't need to make sense. Yes,
Can you just explain again what the indicator function is?
Yeah, so indicator is actually a function. So yeah, very easy to get confused about what's a SOP and what's a function. What it does is it converts a Boolean into a number. So indices equals 1, something like this. gives me a Boolean output. This is a number on the left-hand side, this is a number on the right-hand side that equals, just like in Python or other programming language, takes whatever type is on the left and right and converts it into Boolean. So in this case, integer into Boolean, and this is the output over here. It does the comparison here component-wise. So for every component of indices where the value is equal to 1, we get a true. So we get a true here in the index position 1, and every other position is a false. And the indicator function takes as input one of these Boolean SOPs. So here's a Boolean SOP and converts it into a numeric SOP of 1s and 0s. The reason why you would need to use the indicator function is because somehow you're going to need to do math on the output over here. If you feel like you need to do math on a Boolean thing, that's when you use the indicator function. Very common to, if you have a Boolean expression, to immediately follow it by the indicator function. Does that answer your question? Okay, good questions. So again, the length function here does this weird trick of using averages to convert, to measure the length of something. Not something that you would have to do in any other programming language, because in other programming languages, like in Python, it calculates the length by just actually stepping through the list until it sees how many things are there, or keeping track of the length as you add things or remove things. Those operations not available inside of Rasp, of like changing a variable or stepping through something procedurally. And so we have to do this weird trick of 1 divided by an average to compute the length of something. And so this is something that's built into the standard library. This SOP down here is something that is not built into the standard library. And so we'll see some sort of extension to the length SOP up here with this one. What this SOP does, so first I'm going to copy all this down here so we can just take a look at the output, and then we'll talk about the output and then talk about how it computes that. So this SOP length last location says that whatever our SOP is, or whatever our input to the SOP is, in this case hello, we're still going to calculate the length, but now we're only going to store it in the last location of the output sequence, and everything else is going to be 0. So here last location of hello is a bunch of 0s and then a 5. If we have length last location of ASD, then a bunch of 0s followed by a 3, or add a whole bunch of stuff like this, then it's a whole bunch of 0s followed by 19. And so how do we do something like this? How do we get the 0s everywhere except this last location? Up here on this selector up here, it looks very similar to the selector that we had before. Well, let's just step through what this selector is doing. So there's 2 selectors with an and statement between them, so we'll visualize them one at a time. So this one over here, select indices and length -1. So this length, again, right here has been computed for us. It's built into the standard library. And select indices. So indices 0, 1, 2, 3, 4, length -1, always going to be equal to 4 everywhere. And so we get false everywhere except the last position over here. False everywhere except the last position over here. This length, again, is that SOP that we saw before that has 5 everywhere. When our input is 5, it has whatever the length is everywhere. Indices goes from 0 to the length -1. So in order to get a true value over here, we have to do the length -1 so that length is equal to 5 everywhere, length -1, 4 everywhere. Length by itself, 5 everywhere, length -1, 4 everywhere. So in order to get the actual value of the last index, we do the -1 right here. And compare those with equal, and that gives us the 1 in every location. This is our underscore selector that we saw before for length, the one that well, maybe we didn't see it before. Ignore what I was just saying. So this here is the one in the last location. And then I'm going to take this and like this. This is the diagonal. So indices, comma indices equals gives us a diagonal. This is a common pattern of things that you need to do is to access a diagonal somehow. And the way to do that is indices, comma indices equal to each other. And if I and this together with the first half of this, so the first half of this is the ones all vertical over here. The equals is the ones along the diagonal, and those two together. Then this selector here is going to give me a 1 always in this bottom right corner. And it doesn't matter like how big my example is. No semicolon. Set example ASD. It doesn't matter how big my example is. It doesn't matter how many tokens I'm passing in. I'm always going to have a 1 in this exact bottom right corner. Always have a 1 in this exact bottom right corner with this selector up here. And now this length last location right here, aggregating the underscore selector with indices. And so let's take a look at this aggregate right here. We have -1 everywhere and then a 5 in the last location. The reason for the -1 everywhere is because I'm going to have to add a 1 at the end over here to get the actual length from this last position, because this is the last index. We were doing this on indices right here. What we're selecting is indices. So I do a -1 over here and then add 1 at the end. And that gives me zeros everywhere and a 6 right here. There's lots of other combinations of things that could do this computation, lots of other ways of realizing this result. But this is the one that I came up with when I was thinking about how would I do something like this. Any questions about the mechanics of that? These are.
Instead of substituting -1, why don't you just do you select your indexes to get based on the last position?
Let's see. Well, so if I do this, then what is going to happen, I think, if I remember right, indices +1. Yeah, so this would also have worked. Indices +1 like this, or even just length like that would have also worked. So my code up here is not as simple as it could have been. This was a more simple solution here, this one, or this one. So as I was working on this, what was happening was I was getting a division by 0 error doing something else apparently, and I had to do this subtract 1, add 1 to get the division by 0 to go away. But that was doing some sort of different problem, and I copied and pasted that over here. So my example over here is not as simple, not as clear maybe as it could have been. So you're right, I could have done something simpler. Does that answer your question? Good observation. Okay. We have about 20 minutes left now. So there's some examples down here, but I want to skip down to this visualizing control flow section, because this is where things like the purpose of Rasp is really about this visualizing the control flow and this draw function right here. And this will allow us to start talking about how these Rasp programs translate into these transformer architectures. So we've talked about this length and this length last location, 2 different SOPs that we've implemented. And what this draw is going to do is it's going to show us like a corresponding transformer architecture for both of these 2 implementations. And we'll see that this length last location is going to be more complicated than this length. So let's go ahead and draw length like this. When you do that, it gives you the output still down here, but that's not the important part. The interesting thing is this actual visualization over here on the left-hand side. And inside of the paper, there's a number of visualizations that look like this that are generated from their code and drawing it. The first thing that you can see here is that there's a bunch of yellow boxes here. These are the layers of the transformer. This is an example of a one-layer transformer. We usually don't count the zero layer up here because it's something that's just mechanically computed. Just in this case contains only the indices right here. And one of the things that we can do in Rasp is now we can know that in order to compute the length of a sequence, we just need a transformer with one layer in order to do that. We have provided an upper bound on the complexity of a transformer that can compute the length of a sequence. These layer boxes, they all contain two parts inside of them. This top box up here is what's called an attention head. And the important thing about an attention head is this matrix over here. This matrix over here corresponds to the output of the selector. Every selector corresponds to an attention head. It turns out there are some like optimizations that Rasp does internally that you might have 5 selectors and it gets merged down into three of these matrices, 3 of these attention heads, but you will never get more attention heads than you have select operations. This blue part up here corresponds to the keys. If in the transformer architecture there is a K or key transform that happens, that's this blue part up here. This green part over on this side is the query of the transformer architecture. Down here, there's a bunch of these lines showing a bunch of operations happening. This is the value mapping portion of the transformer. So it's the Q, or the K, the Q, and the V in these parts right here. Normally those parts not explained normally in terms of this Rasp program, but I find that being the most easy way to understand what the transformer can actually do. This bottom part down here corresponds to a feed-forward neural network. There's one up here in layer 0 as well. Layer 0 will never have attention heads, but it can have feed-forward neural networks. And that's what this FF right here stands for, is a feed-forward neural network. And these are anything that is the feed-forward neural network is the element-wise operations. Any element-wise operations you do correspond to the feed-forward neural network, and the selector again corresponding to the attention head up here. The select, I guess, is the matrix, and the aggregate down here. We'll talk more about relating this to the, I guess, traditional presentations of transformers later. I just want to compare some of these different visualizations for a second, and we can get an intuition about some transformers are definitely more complicated than other transformers. So here, the length last lock SOP that we wrote, this is now a more complicated transformer architecture than the length SOP by itself. The obvious reason for that is that it now has 2 layers down here instead of 1, and so in order to implement this, a transformer would have to have a second layer. It can't do this with just 1 layer. We can also see that in my implementation of this length last location, I used this full S internally inside of it. And so that is the layer 1. And this matrix, this selector that I built up down here, this somehow depended on this matrix up here. So that's why it has to be as a subsequent layer farther down the page like this. Maybe one last thing too that I'll say is that, like, in the when we visualize something like full _ S up here in the terminal, the tokens or the things that are labeling the rows in the column are the token labels. But in the actual picture over here, it's a little bit nicer that they put the actual things that they'll be doing the comparison against. Down here, there's 2 rows visualized as doing the comparison down here because this selector happens to be used twice against 2 different these are the query values, 2 different green values down here. Yeah, I guess the main thing to take away from this is being able to get a sense of the complexity so far, and also selectors correspond to select and aggregate correspond to attention heads. The select is the matrix, the aggregate is this stuff down here, and the all the other operations that you do, anything that's component wise, is this feed forward neural network. Yes.
So, for example, in the length, SI is the doing the 1 over the aggregation and then rounding. Is that all inside of the feed forward step?
So here we're looking at the length SOP, and the question is what exactly is inside the feed forward step. There's 2 feed forward steps. So this one right here is the indicator function on indices equals 0. Indices, again, is defined at the layer 0 level without doing any select operations. So we have access to it in layer 0. It does it right here. This is our result of indicator of indices equals 0, like this, 1 with zeros everywhere else. So we get the 1 with zeros everywhere else. Then there's another feed forward operation down here it's actually labeled as length because this is, so the name over here, the stuff in orange, is if you assign a name to it, it is the name. If you haven't assigned a name to it, it's the computation. Here, the name of it is the length, the name right here, the length. And what it's doing is it is the combination of round and 1 divided by aggregate. This stuff right here is what's happening in this feed forward network right here. And you can see here that the output of the aggregate down here is this 0.167. So that's 1 divided by 6. And then the feed forward part is inverting that, taking the reciprocal, giving us 6 everywhere. Is that helpful? Let's see. So I want to talk a little bit the next 10 minutes about some of the more philosophically things. We'll do some more examples here next time, but there's types of attention down here. So what Rasp uses, the original transformer architecture from this 2017 paper, attention is all you need, published in NeurIPS. Another very similar paper, 2019, the BERT transformer architecture. Both of these 2 things are, like, by default what Rasp is actually corresponding to. And both of these, like, standard transformer architectures invented at Google Brain, Google AI language. What we haven't talked about yet is anything related to autogenerativeness in transformers. And there's no citation for this. This is just something that, like, everybody knows as obvious in the field. But there's this variable here I'm calling mask AG. AG standard abbreviation for autogenerative. Mask AG is this less than or equal to lower triangular. And in order to make your transformer autogenerative, so something like what ChatGPT or the Llama models support, where it can actually generate new text, then anytime you use a select operation, you mask it with this mask AG function. Let's see. I think we don't have enough time to do some concrete examples of how to implement that. So I just want to look at some other pictures real quick here on different types of architectures and see how those relate to things. Next time, so again, next week we'll not have class Monday, but on Wednesday we'll flesh out some of these missing parts. The sparse architectures right here, 2 very popular papers. Again, one from Big Bird. The more important one from Google is called Big Bird. This one from Allen Institute of AI, which is basically like a subsidiary of Microsoft, Longformer. Both of these come out in 2020. I spent like 20 minutes trying to find where this was published. Nobody in the machine learning world cares about that sort of thing. All I could find out is that it's on archive. So I don't actually know where it's published. As far as I can tell, nobody knows where it's published. But it's the only thing that's not from Google right here is from Microsoft, the long form architecture. And if we have this function, def mask long former like this, what this does is mask underscore long former. It's going to create me a new selector where this W size here is the window size. If I do something like this, then this is my token attention mask, and it's only going to consider things along a diagonal. So what the long former architecture does, again, we'll do some examples in class next time, is that every time there's a select operation that happens, it ands that with this. So the computation is limited to this like window along the diagonal. The Google Big Bird combines that with a couple of other different types, a random attention mask and a global attention mask. This is the Google Big Bird paper right here. And so they create an attention mask that looks something like this. Anytime, this is very popular in papers to have like matrix sort of looking things. Anytime you see something with a matrix looking thing about transformers, the way that applies in Rasp is that that is the output of a select operation somehow. That is a selector that you're looking at. Let's see. Coming down here, I've posted your homework assignment so you can get started on this. It will not be due this coming weekend. Probably will be due the weekend after that. And my sense is that these problems are all straightforward, as straightforward as something can be related to Rasp. They're all just like basically one-line things, but there will likely take you a lot of fiddling around to figure these out. So in every case, I've given you, just said in some cases it's an SOP, some cases it's a function, and given you some examples about like what the expected input and output should look like. And so you know you've implemented it correctly if your examples actually match my, my outputs down here. So what do I have? I have 7 of these problems that you'll have to complete. I'll probably add more after next Wednesday's class, depending on exactly how much we talk about. But everything here up to problem 4, everything that doesn't say auto-generative inside of it is something that you can do. So up to 5. 5 and below you can do at this point. Yes. Oh yeah, submitting this. I haven't. I don't have an actual instruction for submitting it. I'll post that details, but I want. It'll be you'll create a GitHub repo. The README will contain the details inside of it. That's a good question, and I will have the proper answer to that probably sometime today in the instructions here.
Do you anticipate this being due the Sunday after fall break or the Sunday after?
Probably the Sunday after fall break. So it is, let's see, not the 13th, but the 20th is the most likely due date. Expected due on the 20th. Yeah.
Is the project proposal still due on Monday?
Oh, and then yeah, the project stuff is supposed to be, I originally said Monday, but I was not aware that I made that in the middle of fall break, and so we'll make it Wednesday for the project proposal stuff. And I've intentionally not put up the GitHub issue yet, just so that you all would be able to think about things. I'll put up the GitHub issue for that. We were supposed to reply to that sometime today or tomorrow. Good questions. Any other questions about anything administrative or technical, anything? I will still have office hours Friday. I will not have the office hours Tuesday next week. Yeah, then we'll go ahead and end class a couple minutes early. If you do have questions about anything, I'm happy to stick around and get those answered. Otherwise, I will hope you all have a good fall break.